Over the past 11 years, there have been several large hull losses attributed to control malfunctions, automation anomalies, or instrument malfunctions. This video segment from the Advanced Maneuvering Program will review how we regain and/or maintain control in each of these scenarios. As we look at control malfunctions, topping the list we have rudder hardovers. As many of you in this room probably are clearly aware, there's been a series of events, some of them leading to accidents with the 737 airplane that may be being caused by a PCU malfunction forcing the rudder hard over. However, this can happen on any airplane. You don't have to limit this to a 737 issue. This can happen on any airplane we fly in American Airlines. And the question becomes, what would happen if a rudder, due to a PCU, power control unit malfunction, were to force the rudder full over? If the rudder gets forced over, what's going to happen next? Well, that depends on where you are relative to crossover angle of attack. What we find is that there is a point in angle of attack on these airplanes. There is an angle of attack at which the rudder becomes a more powerful roll control than the ailerons and spoilers are. That angle of attack is not that high. That angle of attack in our fleet aircraft is a medium angle of attack. In other words, in the 7576 fleet, as an example, if you were at flaps 5 plus 40 on speed, you'd be there. You're at crossover angle of attack. At that angle of attack or any higher angle of attack, the rudder is a more powerful roll control than your ailerons and spoilers. What I'm saying is, when you're past crossover angle of attack, when the rudder is fully displaced by you or by a malfunction, fully displaced roll controls in the opposite direction will not stop the roll. The airplane will continue to roll to dihedral effect. All right, I'm going to start off then by talking about what would happen if you just stayed at 1G. Suppose you're at flaps 5 plus 40 on speed. That's crossover angle of attack, okay? And your rudder went full left due to a power control unit malfunction. If the rudder went full left, what would happen next is the plane would yaw, and then because of dihedral roll, you would come up with the yoke trying to stop it. You would get the full yoke displacement and it wouldn't stop. Now in this example, I'm going to assume we stay in 1G flight the whole time. Because if you stay in 1G flight the whole time, angle of attack stays the same regardless of attitude. So we come full up with the yoke. The airplane would continue to roll. It would transit through about 60 to 80 degrees of heading change as it continued to roll. And if we stay in 1G flight, its ground track would look like this. Straight in. Even though you had full opposite roll controls applied, the rudder would do that to the plane. Dihedral effect would do it. Okay, I'm going to show you a couple of videos that the NTSB has recreated of two accidents out there. Now, there is no audio on these videos, so I will have to talk, unfortunately. Okay, the first one is a 737 approaching the Colorado Springs Airport. Now, do not try to watch all of these instruments, okay, because there's no need. This airplane is almost fully configured. All he has left to do is go flaps 30. He's got his gear down. It is visual. They have the airport in sight. The airport's right out here, and they see the Colorado Springs runway. They have it in sight. All they have left to do now is make a shallow bank turn to line up with final, a right turn. Everything's going pretty much normally except for the airspeed needle bounce, which is about plus or minus 8 knots needle bounce on the airspeed. Otherwise, things are going pretty much normally here. Now, when the event starts, we're going to assume that the rudder goes fully to the right due to a PCU malfunction. And then you're going to watch what happens. Okay? In a minute, he'll start his shallow bank, right turn the line up. When he calls for flaps 30, you'll see the nose pitch down. That's normal, right? You call flaps 30, pitches down. Then after they bring the nose back up, that's when the event's going to start. Okay, there he goes. Flaps 30, nose pitches down. The pilot brings the nose back up, and then it's going to start to roll right, and she's going to stop it with yoke. Initially, she'll succeed. There it goes, starting to roll. She's going to stop that with full yoke, and she's going to get it to roll back out. But then she's going to try to pull the nose up, and watch. This is a 737 airplane. He's approaching the Pittsburgh airport. He is at flaps 1 and 190 knots, which is normal speed and configuration for that plane. He will stay at flaps 1 and 190 throughout this event. Okay, I'm going to freeze it for just a second because I want to show you something that's here that wasn't on the last one. On this one, the NTSB put this yoke onto the video. We didn't have one on the last video. Okay? This yoke does not roll. By that I mean even though the pilot may be rolling the yoke, this one won't roll. What this yoke is here is to show you whether he's pulling back on the yoke or pushing forward on the yoke. When he pulls back on the yoke, you will see a shadow develop behind this yoke. The further he pulls back, the longer the shadow. When you pull back on the yoke, what angle goes up? Angle of attack. What empowers the rudder to overpower the roll? Angle of attack. I want you to watch the direct relationship between yoke position and body angles when this event develops. Watch how body angle roll rates increase when alpha goes up and decrease when alpha goes down. We're going to assume, we're rolling now, we're going to assume that when this event starts, a PCU pushes the rudder nearly fully to the left. A controller asks him to call out traffic. He's at 190 in flaps 1, which is normal speed and configuration. Again, when this starts, I want your cross-check to go from the yoke to the plane, to the yoke to the plane. Watch the correlation, assuming that the rudder went to the left. He's about to call out the jet stream traffic in sight, and then the event's going to start. He says, I got it in sight, now watch. Watch your cross-check from here to there. Watch what happens. Yoke, plane. Yoke, plane. Let's talk about the last thing for just a minute because I think it shows us two things. First, assuming we have a full left rudder due to PCU malfunction, you see when you increase the alpha how it increases the roll rate back. It made it roll faster than it would have otherwise, is what I'm saying. And additionally, and also importantly, notice that what happens when you get to 90 degrees of bank and beyond with back yoke pressure. How fast does that bury the nose? How fast did that happen? We have got to unload when we get to 90. Okay, now what we have here is a series of 3 videos. These videos were created by Boeing Flight Test Engineering, and they were very kind to allow me to use these in my presentation. And what Boeing's trying to deal with here is crossover alpha. Now they choose to call it speed because they don't have an angle attack indicator. But you know, and it's very hard to do this with speed. This is purely an alpha issue. Okay, you can only use speed on this issue if you assume the airplane is 1G constant level flight at all times. If you do that, then you can relate speed to alpha. But I don't know about you, but Pittsburgh and Colorado Springs look a little dynamic to me. See? Okay. What we're going to do first is the test pilot. This is a Boeing 737 airplane. What's going on here? What he's doing is he's slowing through 220 knots. Don't worry, I'll talk you through all of that. The important part of this is there's a graphic up here. And the test pilot, there's a rudder pedal here and a rudder pedal here. Normally the rudder pedals are opposite each other. The test pilot is intentionally holding the right rudder fully displaced. And he's going to keep it that way throughout the whole exercise. He is slowing down in 1G level flight at 6,000 feet. And you see that little white yoke? You can just barely see it. He's having to hold that yoke to the left to keep the plane from rolling right to the rudder. As he continues to slow down, as you slow down in 1G level flight, what angle is going up? Angle of attack. So as he continues to slow down and alpha keeps going up, he'll need more and more left yoke to keep the plane from rolling over. Yoke back is represented by yoke down on this graphic. In order to continue to slow down, alpha goes up. Eventually, he will run out of yoke. That is crossover point, you see. When he runs out of yoke, that's crossover angle of attack. I'm going to let this start running. Okay, he's slowing down. He's trying to slow down to 190 knots because that's the proper speed for his current flap configuration. As he continues to slow down at 1G level flight, he needs more and more left yoke to keep this plane from rolling to the full right rudder. He continues to slow now, coming through 205, trying to get to 190. He will never get there. Crossover alpha exists before normal speeds for configuration. As he continues to slow now, coming through 202 knots, you see he's pulling back a little bit on the yoke, trying to keep this altitude. He's also using more and more left yoke to keep it from rolling over. He's almost out of yoke. This is an intentional demonstration of crossover angle of attack. He's now coming through 198 and he's out of yoke. There is no more yoke. It's fully to the left. He's now at crossover alpha. He will now depart controlled flight to dihedral effect. And as long as he keeps pulling back on that yoke, he is history. The test pilot will do this as long as he can stand it. Watch this though, then what he's going to do is he's going to push forward on the yoke. Watch. There he goes. Bam. Yoke forward. Lower the angle of attack. Re-empower the roll. Disempower the rudder. And you can roll out by lowering alpha. Okay? In the dive, he gains 90 knots. With the extra 90 knots, he can go back to 1G level flight at a lower angle of attack. Even though the rudder's still in and it takes a whole bunch of left yoke, he's back under control because the alpha's lower at the higher speed. Okay? Everybody follow that through? Now what he's going to do this time is he's actually flying at 190 and flaps 1. Stable, configured. Okay? He's going to do what we call a neutral start. By that I mean everything's symmetric. He's rudder opposite each other. Everything's neutral and symmetric. The yoke is level. The thrust vector is level, symmetric. Okay? Everything's stable. Now what he's going to do intentionally is slam full left rudder. Then he's going to take a 3-second human factors delay, and he's going to go full right yoke against it and try to stop the roll. But then he's going to do what airline pilots tend to do. He's going to try and maintain 6,000 feet. To do that, he's going to pull back on the stick. Watch what happens. Bang, full left rudder, yaw, roll violently. 3 seconds later, right yoke against it. Pull back on the yoke in order to maintain altitude. And say goodbye. The rudder is the most powerful rolling force in your airplane. Don't worry about the test pilot. He's got this all planned out. It's his can. Okay. Now, what he's going to do this time is very similar except for one issue. Okay? He's going to do the same neutral start at the same altitude, at the same speed. And again, he's going to slam full left rudder. 3 seconds later, he's going to go full right yoke. But this time, he's going to say, to heck with altitude. Instead of pulling back on the stick, he's going to push forward and lower alpha and immediately regain roll axis control, although we'll have to give up some altitude. Here we go. Bang, left rudder, yaw, roll. 3 seconds later, right yoke. Don't pull back, push forward and immediately regain roll axis control by disempowering the rudder by lowering angle of attack. In the little dive, he gains 70 knots. When he's going 70 knots faster, he can fly at a lower angle of attack. Even though he still has full left rudder, and it takes a whole bunch of right yoke, he's back under control. Okay, that was a nice sequence of events. It was canned, but it was worth doing, I think. Where Boeing flight test is showing in a sequential manner the consequences of these various acts and effects if you were to have a full over rudder. Having said that, I would submit to you that it has no application in reality. Why? Well, as highly experienced aviators, I want you to think about this with me. I'm going to suggest to you that as we're out there flying along in our airplane somewhere, someplace, could be anywhere, let's say flying somewhere, entering the traffic pattern off of approach or whatever, our airplane starts to roll. I'm going to submit to you that I, for myself, and I think if you think about it too, at this instant probably don't have any idea why it started to roll. I mean, it could be rolling because as I configure, my flaps and slats went asymmetric. It could be rolling because I hit the vortex of the guy ahead of me. It could be rolling because of an engine failure. You see? At this instant, I doubt I'm smart enough in most situations, and certainly in the weather, to understand clearly at this instant why it's rolling. All I know is it started to roll. It's an uncommanded roll. My job is to stop it, right? So I come up with some yoke and say, come on, stop rolling. But it doesn't. So I come up with some more yoke and say, come on, stop rolling. And it doesn't. Well, what control would I go to now if this isn't stopping a roll? Yes, rudder, sure. So I come in now with coordinated rudder, right rudder in this case, trying to roll right. I come in with coordinated rudder. Now, you've got three possibilities here. The PCU can fail in three different modes. The power control unit, depending on where the slide valve is. And so let's take the best case scenario. You come in with rudder, and the rudder regains rudder, the rudder pedal regains rudder control with the other PCU or PCUs, and the rudder comes back. Great. Rolls out. End of problem. Now, let's get back to that same point and take one of the two remaining scenarios. That is, you come in, this time you come in with right rudder, and you will feel a definite resistance in the rudder pedal. It doesn't want to go in. Well, your rudder is going to stay left in this scenario now. But at least you have some idea why, right? Because of that rudder restriction. Now let's take the worst case scenario. It started to roll, you came up, you came up, came up, you came in with rudder, and the rudder pedal goes in, but it actually pushes the rudder further left, even though you put in the right rudder pedal. That's the slide valve went all the way across. And so now you're pushing the right rudder, which will push the left rudder even further than it already has gone if it's not all the way to a full deflection. Okay? And so now I suggest to you, and I think you would agree at this point, I don't have the slightest idea what's going on here. I've pushed in right rudder, I've got up this, and this airplane is still rolling over. Okay? And so now I get right here. Quick. American Airlines procedure. Is this nose high or nose low? And are you at 90 degrees of bank or more? What do you do with this stick when that happens by procedure? You push on it, don't you? Right? You unload, you go neutral by procedure. So I apply the procedure that we're being taught, and I don't know why, but I got my yoke over here, I push forward, guess what? The plane starts rolling out. At this point, I suggest to you, I probably still don't know why. But it starts rolling out. Great. Now, if I get too aggressive about trying to get the nose up, I go, whoop, whoop. I get it. See? Probably for the first time, I'm getting it. This airplane's in a slip. And I can't do that. So, but now I'm picking up speed, and I raise the nose more gingerly, more carefully. I get it back up because of the extra speed. I'm able to fly now at 1G at a lower alpha, and even though I've got my yoke way over, I'm under control. And I realize that I'm in this big skid or slip, and I probably have a rudder malfunction. Well, what did we just do here? We just flew the plane first. We regained and maintained control by applying proper piloting skills and procedure. Then, having regained and maintained control, we identify the problem and we treat it. Well, I've got a left rudder. And there's procedures in your book, disconnect the yaw dampers and these other things, trying to get your rudder back. So let's take the worst case scenario. You can't get the rudder back. You go through the whole procedure for your particular airplane and the rudder is still to the left and your yoke is still to the right. And you're flying along like this in this big slip. Let me throw it out to you with all that we know today, to you guys and gals. What can we do with the rudder not coming back? In other words, we're going to assume the rudder is going to stay to the left. what can we do, what tool can we use to return to symmetric flight? Exactly. Right on. Thrust vector effect. We will advance the left engine and retard the right engine. In this case, with the throttles, and using thrust vector effect, we will overcome a full left rudder, return to symmetric flight, yoke level. Now, let me say something. Don't get clever early. Okay? I have no time to tell you all the ways you get in trouble doing that. Fly the plane first. Regain and maintain control. Identify the problem. Treat it. Okay, let's look at slat abnormalities. You know, suppose during the process of deconfiguration after takeoff or reconfiguration on approach, you go asymmetric on your slats and all the slats are out, let's say, on the right wing and they're all in on the left, as an example. If they're all out on the right wing, you now have a high lift wing, don't you? So the plane's going to roll, isn't it? And as it starts to roll to that high lift wing, you're going to come up with yoke. And if yoke isn't doing a real good job at stopping this roll, what will? The rudder, sure. We come in with a rudder, we can stop the roll. We come in with some more rudder, we can roll it out. We come in with some more rudder, we can get our yoke level. And then we say, what happened? Oh, we got slat asymmetry. Great. Let's get out the checklist. Treat it. But we flew the plane first. Let's look at flap abnormalities. There's several of these out here, but you know, I'm going to tell one about us. I'm going to tell a story about American Airlines here. The reason I'm going to tell a story about American Airlines is because it's going to lead into some things we're going to talk about this afternoon. This issue of automation dependency, you know. Where was it, 15 years ago or so, where we started talking more and more about automation, and we more and more started focusing on buttons to push to fix an errant flight path, or typewriters to type in, or switches to move, or levers to reposition, rather than flying the plane? See? Because it started. It wasn't our fault. The whole industry embraced it, and we just went down the road with everybody. But it definitely crept in. Let me give you an example. The example relates to, in this case, inboard flap asymmetry. 10 years ago, when I was a 767 check airman, we had no 757s in American Airlines at that time. And then 9 years ago, we got our first 757. Airplane was coming, and before we got the airplane, we got a CAE simulator for the 757. Well, as check airmen, corporately, we view that simulator as a toy. I mean, we jump in there, we want to find out how it flies, and then we want to push every single fault button in the simulator, see what happens, and how you deal with it. So corporately, our check airman group is doing that very thing with this new 757 simulator when they come to a button that says inboard flap asymmetry. So they push it. And when they push it, what happens in the simulator is the right inboard flap goes down and the left one doesn't. And they find out something very interesting. On a 757, this is an eye-watering roll. It is the worst rolling fault for asymmetry I know of any in our fleet aircraft. And when you come up with the yoke, it doesn't even slow down. See? Well, watch what I just did there, okay? We call Boeing Aircraft Company and we say, hey, Boeing, do you know that when you have an inboard flap asymmetry on a 7.5, this guy really goes for a trip? And Boeing says, well, yes, that would be true, but that can't happen. We have blockers and doofers and ding-fang-doos right in here, and they're not going to let those flaps split. And we went, really? So then we had a meeting. I'm talking corporately. There's no individuals here. Corporately, we have a meeting, and we say, well, what are we going to do? This is the worst rolling fault we've seen for asymmetry. This won't slow it down. There's no button you can push that we know of, or thing you can type in that will stop this. You'd actually have to fly the plane. And Boeing says it can't happen. So you know what we did? We decided to remove it from the simulator. That's right. That was our corporate decision. Since there was no button you could push and nothing you could type in and no lever you could move that would stop this thing, we said, let's don't spend any time teaching our pilots to fly planes. We're automation managers. Just move it out. That's how we were thinking. That's how we had started to think. See? And so what happens next? Well, as you know, 3.5 years ago now, out there in the real world, Boeing 757, other companies, 2 of them, one on the ground, one in flight, the thing that can't happen, happened. Inboard flap trip, symmetry. And the guy in flight, what happens is the right flap goes down, and what I told you before, he can't even slow it down with the yoke, okay? Now, this captain does do something intuitively correct. I agree with what he did. He takes the flap handle and moves it back from whence it came. Okay, that's good stuff. And fortunately, the flap that was going down comes back up. So as he holds the yoke like this, the plane kind of dishes out like that. All right. Now, what do we do at American Airlines? Well, we see, of course, our safety net picks up on the fact that the thing that can't happen is happening. And we get real excited. We go, gosh, we've got to tell all our 757-6 pilots about this. They've got to know. So we put a whole bunch of pink bulletins together very hurriedly to launch them out to all you guys and gals saying, hey, the thing that can't happen is happening. But do you remember what we said in that pink bulletin to do if it happens to you? Anybody remember? You may not have been on the fleet then. What we said in the pink bulletin to do, if this happens, we said, move the flap lever back from whence it came. A mechanical fix. Do you see a problem here? Does anybody see a problem? I mean, the plane's rolling, you come up with this, and you move the flap handle back. I mean, yeah. What happens if the flap doesn't come back up? Well, then just die like a man. You know? I mean, what are you whining about? You know, I think all you guys and gals know where I'm going with this, and I think you understand the point. What should we have done 9 years ago, when we realized what a terrible rolling fault this was? What should we really have done? And I think you all agree what we should really done is, if you find out that this yoke won't stop this plane from rolling, what will? Rudder. Even with this fault, if you come in with rudder, you can stop the roll. If you come in with some more rudder, you can roll it out. And if you come in with some more rudder all the way to the floor, in this case, with the rudder, you will just get your yoke off the stop. That's how bad it is. But you've got it. You've got it. You're under control. And then you identify the problem and you treat it. But you fly the plane first. But 8 years ago, we had already started to drift away from that philosophy. Okay. Let's go into the pitch issue. Let's go away from the roll axis and look at the pitch axis, okay? Let's talk about stabilizer stuff for a minute. Unscheduled or jammed. You might be interested in knowing that unscheduled stabilizer accounts for 4 hull losses and 282 deaths in this time frame that we're concerned with. What is unscheduled stabilizer trim? Well, remember back in the 7.2-osaurus, the Jurassic jet? Unscheduled, some of you are still there. So remember, unscheduled stabilizer trim was obvious to the most casual observer, wasn't it? Right? I mean, that big old wheel down there, right? Spinning around, clanging and banging, right? In a manly way, you're supposed to put your hand on it, bring it to a stop, right? Yeah, or grab the co-pilot's knee and jam her knee in the other side. Everybody knew what was going on, didn't they? See? But you see what killed those 282 people? Is a very insidious event. Because today in a highly modern automated airliner, unscheduled stab trim is essentially unseen and unheard. But it's happening. Let me give you my definition of unscheduled stabilizer trim in a highly automated airliner. This is a little convoluted, but listen. The stabilizer is currently running in a direction that is opposite to the way the pilot flying would intuitively believe it to be going. You get it? Usually to an autopilot command, but sometimes to a fault. Let's look at one of those accidents. This is an Airbus A300-600R approaching Nagoya Airport. It's the exact same airplane that American Airlines flies. Behaves essentially like any of the airplanes built this way. Okay? He's coming in to land at Nagoya. It's visual. He has the field in sight. The co-pilot's flying. He has the auto throttles on and the autopilot off. He's trying to hand fly, and he's coming on in, and he's got the ILS tuned up so he can get the glide slope, which is great, and he has the field in sight. As he starts to work onto the glide slope, he has a little trouble with his glide path control. Okay? And as he has more and more trouble getting stabilized on the path, he does something that we see automation-dependent pilots doing more and more. He goes, I don't fly much. I'm not very good at this anymore. He goes, autopilot, would you help me with this? But then he goes, no, I can do it. And he goes back to hand flying, and now he's hand flying the airplane coming in. What he doesn't know, though, is in fact there is an autopilot engaged by his action. So as he continues to fly the airplane, neither he nor the captain, knowing an autopilot's engaged, they think they're hand flying. They're coming down to land. He gets his glide path under control, gets things kind of stabilized here. And then one of the two pilots, they don't know which one, accidentally nicks that toga bar on the auto throttles, right in front of the throttles there, and puts it into the go-around mode. And this guy's still coming in to land. Well, since he's coming in to land, the co-pilot, and the autopilot's on, and it sees a toga command, the autopilot goes, well, gee, this guy's got the elevator and the throttles. How am I going to go around? So then the autopilot goes, oh, I know. Yeah, I'll go around with the stabilizer. So the autopilot starts running the stabilizer toward nose up in an attempt to go around. The first officer who's flying, see, he's coming in to land. And so as he comes into land, as you might imagine, he's having to push farther and farther forward on the yoke because of this stab trim run. And as that disparity gets great enough, that conversation in the cockpit starts. And all you guys and gals know this conversation between the captain and the co-pilot. You know the one that goes, what is, why is, how come is? Well, that's going on in the cockpit as this thing's running, and finally it comes to a stop within 1 degree of full up, because that's autopilot limit. At about the same time, the first officer hits what is essentially full nose down elevator limit. So they're even. And they're still coming in to land. See? Well, then another neat thing occurs. The auto throttles, without telling the whole story, the auto throttles are commanded to be engaged, and they engage into the go-around mode. When they engage into the go-around mode, the throttles go flying forward, right? When the throttles go flying forward, what do they say that would do to the pitch axis of an airplane like this? Sure, I see all your hands doing it before I even said it. The airplane starts up. Well, does he have any more elevator left to deal with that? He's already used that, hasn't he? So now he's holding the elevator full forward, but the thrust vector is bringing the nose up and up and up. The captain gets on the yoke, and he's pushing full forward on the yoke. And the nose keeps coming up. This goes on for the longest time. Think about this, guys and gals. They're both holding the yoke full forward, and it goes on and it goes on and on. Neither one of them has any idea what to do with this. It keeps coming up and up and up and up and up. Finally, it runs out of energy up in here, stalls, comes down, tries to lift again, right wing stalls, rolls over onto its back, and goes into the ground 80 degrees nose low. I'm going to compare that, since we have our Delta friends here, I'm going to compare that to an incident that occurred with Delta that leads their crew to the exact same problem. I think you will agree. However, they deal with it much better. This is a Delta 1011 airplane built like this. This will be an example of jammed stabilizer. However, I think you will agree it took the crew to precisely the same problem. They're taxiing out in this 1011 at the San Diego airport here a few years back. We wrote this up in Flight Deck. Many of you may remember this. They're taxiing out in this 1011 at the San Diego airport, and as they taxi out, unbeknownst to the crew, the stabilizer runs fully up and jammed. And they would have had no way of knowing that. And it's fully up and jammed now, and as they take the runway, they can't know it because as part of the fault, the stabilizer trim indicator is still in the green takeoff range. Yeah, the plot thickens, doesn't it? So as they taxi onto the runway now, it indicates that they're in the green on takeoff on the stabilizer, and now when the first officer who's going to make the takeoff pushes the throttles up for takeoff, there will be no takeoff warning horn. Because as you know, the horn is tied to the indicator, not the stabilizer. So they go roaring down the runway with no warning, and the airplane, of course, starts to rotate early. And the first officer does what I think I would have done probably. He goes, come on, stop that. I'm not ready for that yet. And he pushes forward on the yoke. But the plane rotates some more. So he goes, come on, stop that. And the plane rotates and lifts off at the same time he hits full forward yoke. They're airborne with full forward yoke, and they're not even at rotation speed yet. Ooh, right. From here on, it looks a whole lot like Nagoya. Now, by the way, the captain, to his credit, is on the voice recorder already trying to run the stabilizer trim, which I don't think I'd have thought of it that fast, but it doesn't matter. That it wasn't going to move. It was jammed. So they're holding full forward on the stick, the first officer is, and here comes the nose. It's coming up. It's coming up. Quick, somebody else. Is this unusual? Is it nose high or nose low? What should I do? Help me, quick. Yes, roll, yes. And the captain takes over the airplane, says, I've got it, and rolls the airplane to a nose-high, unusual attitude recovery procedure that I promise you he was taught by someone somewhere. Because when you roll the lift vector off, regardless of what is wrong with an airplane, the nose is coming down. He applies that procedure, he gets the nose coming down, he rolls back up, and she just clears Point Loma out off San Diego, the ridge. And she's back in the climb again, of course, because the fault is still in there. So he goes up to another nose-high unusual attitude recovery, and then he goes up to another nose-high unusual attitude recovery, and goes up to another nose. He corkscrews out over the Pacific Ocean, doing one nose-high unusual attitude recovery after another. Finally, he gets enough altitude below him where he thinks he can start dealing with this problem. And besides, everyone is puking. So he starts saying, okay, what am I going to do with this horrible pitch problem? With an airplane built like this, what's the first thing you'd go to for a horrible pitch problem? Exactly. Thrust vector effect. And he does. He pulls 1 and 3 to idle. He jams number 2 to max. And bang, he overcomes a full-up stabilizer, and he regains normal pitch control. Just one problem: not enough total thrust. Headed back for the ocean. Okay? So he has to come back in on 1 and 3. So he leaves number 2 and max. He eases back in on 1 and 3 until he finally gets enough total thrust to stop sinking. Now his airplane's back to doing this, but not nearly as violently as it was before. Okay? And then he says, well, what else can I do to deal with this pitch problem? He thinks about it for a minute. He says, I know. I'll move the center of gravity. So he picks up the mic and he says, free drinks in first class. Yeah. Everybody in the back runs to the front. Okay? You get them all up front, and guess what? He gets this puppy down to a pretty nice little damp, okay? Now, I'm going to stop right there because this story takes too long to tell in its entirety. But let me go on to say that this captain goes on and does several clever things that every pilot in this room would think of given time. And he recovers this airplane in a very boogered configuration successfully at the Los Angeles airport. Right? Sure. Whoever he is, he just got applause. The point here is that I want to make, and I think you guys and gals get it, is what's the difference between Nagoya, the outcome at Nagoya, and the outcome at San Diego? Training. Because see, right here, few of us, certainly not I, are clever enough because there isn't time to be clever. A critical flight attitude recovery requires training and rote response because there isn't time to think. You must respond to the training. And it's that response to that training, that initial move, that saves the initial crisis, that buys the time to do all the clever things that we'll all think of given time. Buy into that?